For the simply supported beam shown, draw the shear and bending moment diagrams and determine the max normal stress due to bending. So I want to draw this just a little bit differently now, using the relationships between the shear and bending moments. Okay? So I'll put this over here, and then I want one more right here, right here. There you go. So we put that over there. We first have to find the reaction forces. So let's do a global equilibrium. So what's the first thing we're going to look at? I'm going to do the sum of the moments, where I'm going to say positive in this direction about the point A are equal to 0. Well, what does that mean? Well, that means that if I do 3 times the total length 8 at a position of 4 from A, and that's going to be negative. And then we have another negative 12, keeps feet for that concentrated moment, and then a positive by times the total distance, which is 8 plus 4, which is 12. All of that must be equal to 0. So let me calculate that real quick. So it's going to be 8 times 3 times 4 plus 12 divided by 12. So 8 times 3 times 4 plus 12 divided by 12. That's going to be 9. So By equals 9. So Ay equals what? Sum of the forces in the y direction must be equal 0. So that's going to be what? It's going to be minus 3 times 8. I don't want all these parentheses. So minus 3 times 8 minus, no, I'm not going to put the 12, plus 9. So all of that, and then we have our plus AY. And that's equal to 0. So AY is going to be equal to 24 minus 9, which is equal to 15. Right? 24 minus 9 is equal to 15. Right? Kips. So, remember that the derivative of the distributed load with respect to the length x is my bad. The derivative of the shear force with respect to the length is equal to the negative of the distributed load, which if we integrate, this is a separable differential equation, so dv equals minus w dx, and we integrate on both sides, we get v at, so we're going from A to C. From A to C. So really, what do we get? Well, sorry, we're not going to have the integral anymore. We're going to get VC minus VA is equal to the negative of, well, this means whatever is the area under the distributed load from the portion A to C, which is 3 times 8, which is 24. So this is 24. And so we have VA, so VC is equal to minus 24 plus VA, which is equal to minus 24 plus, well, what's the shear at A? Oh, that's my reaction force. it is 15. And so what we get is minus 9 kips. Now, let's do the same thing for the moment. So the derivative of the moment with respect to x is equal to the shear. So that means that the moment integral from a to c is equal to the integral from a to c of v dx. And now we're going to get mc minus ma equals to what? It equals to v, which is the shear. It equals to the area under the shear curve. So we need to plot the shear first. So let me do that. I'm going to have this right here, and then I'm going to have another one for the moment, and I'm going to have to extend those lines. So this line must be extended, and this line must be extended. So now that we've extended these lines, what are we going to do? Well, this is going to be my V, and it's going to be in kips. And so I'm going to start at 15. So I'm going to go to 15 here. And then I'm going to decrease to -9. So -9. And so what's the area under the curve for this? Well, it's going to be 15 times... Oh, we need to find when that's equal to 0. And when is that going to be equal to 0? Well, we're going to have to say... What are we going to have to say? Because we don't have the length of this. So we can't really calculate the area right there. So what are we going to do? I got to think for a second. So we're 15, we're going to -9. We don't have the position 0. So we kind of have to find that position 0. And so that's kind of like saying 3 times x, 3 times x, three times x, and it's negative. That's going to be my shear. You kind of have to find the shear. So my shear is going to be -3 times x plus whatever we started with at a, which is 15. So now you want to know, when is your shear 0? Well, that's going to be at 15 divided by 3. So at 5 feet. So this is 5 feet right here. I don't know, I feel like that's cheating though, because we used the equations. But now we know the area at the top, which is going to be 15 times 5 divided by 2. So 7.5 times 5, which is 37.5. And then at the bottom, we're going to have 9 times 3 divided by 2, which is minus 13.5. And so overall, we have a change in the moment of 37.5 minus 13.5 of positive 24. So that's going to be 24. And we know that this is 0 because the moment starts at 0. So we can say that our MC is equal to 24 KSI. No, kips times feet. And now we can plot it. And let me ask you a question. Is it going to be, it's going to have a concave up or concave down? It's going to be concave down. So we're going to have a slope that goes up and then back down. Intersects right here, which is the point 24. And then from there, what happens? Well, then the shear there stays constant. And then it looks like it's going to have to go back to 0. In fact, B is 9. So that means that this one right here, we can actually use the same formulas as before, and we can say VB minus VC is equal to the area under the curve, which is 0. So VB is equal to VC, which is equal to minus 9 kips. And then for M, do MB minus MC is equal to the area under this, which is 9 times 4 is equal to 36. And MC, we've already said, is 24. So MB is equal to 36 plus MC, which is equal to 36 plus 24, which is equal to 60, right? 60. And so now that's kind of confusing because we're supposed to go down, not up. We're supposed to go down, and then that brings us, so we're supposed to go down 12. So if you do 24 minus 36, 24 minus 36, you're going to get minus 12. So these have to have different signs. And that's because I didn't put that this area is negative. So that would be minus 12. Kips times feet. And so then we get to here, we'd go to negative 12. And then here we'd get to 0. And so now they want to know, what is the max? Well, we know that it happens at 5 feet. So now we can say M max is going to be equal to, and we need to have the equation again. So the moment about the cut is going to be 3 times x squared over 2, negative, minus 3 times x squared over 2, plus my reaction force at A, which is 15 times x. We just said that my x is 5. And so my max is going to be at minus 1.5 times 25 plus 15 times 5, which is 37.5. 37.5 kips times feet. And that's going to be right here. 37.5. And so now we can find the max normal stress because we have the cross section. So that's going to be minus 37.5 kips times feet times 12 inches in 1 foot. Distance, max distance from the centroid is going to be 10 because it's 5. because symmetric, and then we have 1 over 12 times 3 times 10 to the third for the moment of inertia. And so when we put all that together, minus 37.5 times 12 times 5 divided by 3 over 12 is the same as 1/4, so 10 to the third divided by 4. We get minus 9 KSI, so that's compression, and that's what they wanted to know. All right, I hope this was useful, and I'll see you next time.